All right, thank you for coming to this presentation, cache-friendly data plus functional plus ranges equals love. The mic is not on, okay. Okay, do you hear me now? No? No? I can shout. He was very careful in telling me to be punctual. Okay, better? No? No? Ah. One of the great joys of speaking at events like this. Try now and see. Do you hear me now? Yeah, I hear an echo. Okay, good. So, thank you all for coming and welcome to this presentation, cache-friendly data plus functional plus ranges equals love. I should say right away that if you are the kind of programmer who is intimidated by angle brackets and parameter packs and indirections, there were so many indirections, you probably want to be in another talk. Otherwise, enjoy. A little bit about me, I'm Björn Fahller, I live in Sweden. I am fairly new to this programming thing. I've been doing it full-time since '94, most of this in C++. I currently work for NetInsight in Sweden. We do networky things like these machines. They are used, for example, to keep time in 5G networks. 5G networks require extremely precise time, and we keep nation-state size networks within a handful of nanoseconds. So NTP, but a million times better. Or media networks. You have a huge one here in Norway, actually. Media broadcasters love these. If you have watched any live televised event in the last 10, 15 years, you have probably indirectly used our equipment. So that is the kind of stuff that I tend to work with daytime. But let's go into the topic for today. The inspiration from this was primarily a talk by Mathieu Rapin about the data-oriented design and entity component system, where he talks about how you lay out your data and how you access your data, implications it has. And that talk, in its turn, was very much inspired by Mike Acton's amazing keynote from CPPCon 2014, so 10 years ago now. I had at that time actually not watched Mike Acton's keynote, so I did. And he has some really, really interesting thoughts about how you let your knowledge about how you access your data drive your design so that your program has efficient data accesses so that it's fast. The code he shows in that presentation, however, is a crime. But the ideas are good, so if you haven't watched it, do. You will learn from it. It's really good. But as I was watching these, I couldn't help thinking, it should be possible to do better. It should be possible to make something that is easier. So the basic idea with this, say that I have this struct S with some members, X, Y, Z, and D, and I have a vector of them, and I want to search for a struct where D has some specific value. So the way it does it, we do a memory read, and this is about how the hardware works. You never read individual bytes of memory. You read a cache line. So typically on today's CPUs, that is 64 bytes. You read 64 bytes at a time, and then you look at the first D. No, it's not that one. Maybe this one. No, it's not that one. Do another read. Look at the, no. Okay, another read. Look at this D. Yeah, that is the one. Now we can access the other data members. The problem with this is that memory bandwidth is a limited resource. And in this toy example with just a handful of accesses, it really doesn't matter. But imagine that the search was a few hundred, maybe a few thousand elements. Then we have utilized about 1/4 of our available memory bandwidth. And what's worse, every time we read from memory into a cache line, it means that that cache line held some data. It will be evicted, which means that the rest of the program will have less of its data in hot cache. So your program will be slower. Compare that with having a struct of vectors instead. So I have a vector of x's, a vector of y's, a vector of z's, a vector of d's. And I do the same thing. I do a read, check, is it this one? No, 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 no. Another read, this one? No, no, no. Yeah, think that. And then we access the other ones. Again, in this tiny toy example, it doesn't matter. But if we had to search for several hundred Ds, it would make a difference because we're essentially not wasting any of our memory bandwidth. Every byte read is used, except for the last one where we actually found what we were looking for. So let's have a look at this. So I have a toy example here. So I have a vector with objects. I populated with 1 million objects. That is kind of excessive, but it means that I will get numbers that makes a difference, visibly so. So I populate with a large number of values, and then I check. I just run this loop where I call drop everything where z is less than start, and I begin with 100, and then I increment these. And drop if, this function, it calls the predicate, and if we find it, then we take the topmost element, move it to this slot that we're not interested in anymore because we want to remove it. Otherwise, increment the index to search for. So go upwards, upwards, upwards. Okay, drop this one. Upwards, upwards, upwards. Drop this one, etc., etc. So I can build this, and for these examples, I'm using Clang 18, and I'm using C++ 23. The compiler is pretty picky about the compilation flags. So I'm building with vectorize and setting the architecture to native, which is probably not what you want to do in production, but that is to ensure that the code is generated for this actual machine that I'm running on. Otherwise, the compiler is very conservative about what it is allowed to do. And since I'm a Linux person, I use perf for these. So I run this program, and we see some numbers that doesn't mean anything yet, but this is a baseline. And then I have another program that uses struct of vectors. So we have our struct S here with all the x's, y's, z's, and d's. And the logic here, pretty much the same, drop if the value of x at the index is less than start. This becomes a little bit more convoluted because I don't have access to an object. So I have to give the predicate the S, the struct that has all the vectors, and which index to look into. And of course, we can see that the drop if is, I wouldn't say it's very nice code. But yeah, if the predicate hits, then we again move the last element, move the last element, move the last element, vector by vector. So the logic is the same. So if we build this, and run it, now we can compare some numbers. So Vector of structs, 2.5 billion cache references compared to 641 million. Okay, that is a substantial improvement. Cache misses less than half. Instructions fewer. CPU cycles a little bit fewer. Branches roughly the same. Time, well, it's faster, isn't it? 2.2 seconds instead of 2.6 seconds. It's faster. So what we can see here is that structure vectors has way fewer memory accesses. Way, way, way fewer. Fewer cache misses. That is important. Slightly fewer instructions, not a huge difference. It's faster. I would actually have expected the speed up to be more, given the reduction in memory accesses and cache misses. But there you go. But it is faster. And it's absolutely horrible code. I don't know about you, but I don't want to work with code like that. I just don't. So I really had to think, can we make this easier to work with and keep the performance? It should be possible. So I made an experiment. I used tuples. I create a table type, a table of t's, and it has this tuple of a vector of t's. So that is the way we get all the columns of data. And I use a row type that is a tuple of references. So when you use operator angle brackets to get a row, you populate it with references to the cell in each of the columns. And by then adding some more, we need to push back, pop back, get the last one, reserve is good to have, check if it's empty and the size. And then we can write a drop if that looks like fairly reasonable code. You just loop over the elements, call the predicate on the element at the index I. If it's found, then move the topmost element into where we are and pop it. Pop the vectors, all of them, pop the last element. Otherwise, go up. So now we're doing pretty much the same as before, but we have 4 in parallel, like this. Okay, move that one in, pop, pop, pop. Like so. And the drop if function can then look like this. I can use destructuring to get the X, Y, Z, and D members to write logic in a way that is humanly readable. So let's have a look at this, the templated solution. So here is the table, as I showed you, with how to store the elements, pop back the operator angle brackets, get the last one, reserve, etc. So you just call every operation on the table is expanded to the similar operation for each of the vectors. And then the logic looks like this, which is pretty okay, I think. So let's have a look. $640 million, 11 million, 313, a bit fewer instructions, good. Many fewer cycles. Branches, roughly the same. No, branches is actually quite a lot lower, sorry. Branch misses roughly the same, but the time is curious. This is curious. I don't understand this. To me, these 2 examples, the previous 2, they are in every way equivalent. But for some reason, the previous one was 2.2 seconds, and this one is 1.6 seconds. I know sort of why the compiler generates more vector instructions, but I don't know why it generates more vector instructions. This is curious. I'm not complaining by any means. I'm really not complaining. This is good, but it's surprising. So what we can see is definitely that the ergonomics of using this very simple toy table is roughly the same as working with a vector of structs. But the performance is quite a lot better. So when I had reached this point, I felt that I'm onto something. I can do something. So I wrote an abstract for a conference presentation and a very cocky title, and here we are. So, but to be happy with this, what we also need is we need a stable row ID, because that is one of the things with the entity control system. You want to be able to store an object, and you want to be able to get an object by some sort of stable handle again. This can be done in several ways. One way you can do this is to keep track of which slots, so to speak, which indexes in your tables there are used for data and which are not. So when you erase something, you just mark a row as free. It's available. And when you insert something, you see if is anything free, and then you drop it there. Otherwise, you grow it. The advantage of this is that insertion and removal are really fast. But the disadvantage is that you can essentially not really use vector instructions for anything, because you have to, as you iterate over your columns, you can see, okay, here's data I want to use it, here's data I want to use it. No, this is a free index, I'm not using that. And then you go to the next and the next. Can I use this? No. Can I use this? Yes, etc. Another way of doing this is to store all data like I showed you in these examples now, where removing something, we take the last element and pop it into the removed row. This has the advantage of keeping everything in contiguous memory. You can use vectorization, but the disadvantage is that as you remove elements, your data becomes jumbled. The iteration order is not the same anymore. Plus, as we will see soon, there will be an overhead on how do you translate the object ID to where it actually is located, since the elements move around. With the previous example, where we just mark a row as available, then the row ID is the offset. We'll get back to that soon. Definitely want an iterator interface so that we can work with standard algorithms and ranges, so that we can express our logic in terms of what we want to do instead of in terms of the mechanisms used to achieve it. But also, to be happy, I want more. I want a convenient way to look at only some of the columns. Not all expressions will use all of it, like we saw the searches for just the D or just the Z. I don't want to bother with the others. And I want a convenient way to call functions with the elements of a row, or rather with the selected subset of elements of a row. That would be cool to get. But this is good enough. The successometer is on a smile. So let's see what we can do. So stable row ID, like I said, I've chosen to go with compacted storage by moving elements to the end, and therefore I need an extra column. I need the index. So, for example, if I want to erase the D's here, what we do is we see that offset 3 is now free. I can plop the I's into there, but now we used to know that the I's were on offset 8. So we see that on offset 8 in the index, we can write a 3, so that when you want to access, we can skip that for now. When I want to access row ID 3, we follow access row ID 8, sorry. We see that on row ID 8, the index says it's on offset 3, so we follow that, and then we find the eyes. And then I also need a reverse index, because if I have done some searching and found, here are the eyes, what's the row ID for that? Then we can see that it says, the reverse index says, it's number 8. On the stable row ID is 8. So the index and the reverse index are always pointing to each other. So if I now want to add more data, I want to add case. Insertion is sort of simple. You always add the data at the end. So, and I know that it should be on stable row ID 3 because that was the first one that was available. So I can now write 8 in the index. And I keep track of where is the first free index to use. Currently, there is none in this picture, so it needs to grow the index to store something more, because it's number 9. And again, index and reverse index are pointing to each other. So I can now write like this. The operator angle brackets, we need to go from a row ID to a storage offset by looking at the index. And the rest is exactly as before. And now I can change the API a little bit. So pushback gives me a row ID. I have operator angle brackets with row ID. I can erase with a row ID. And I can ask, do we have this row ID, actually? So I can then write things like this. Push a number of values. I have the row IDs I1, 2, 3, 4. Erase I2 and I3. I can look up I1 and I4 and see that they are indeed the expected values, even though they have been moved around in memory. And I can check that I2 and I3 are not valid row IDs. Because if you try to look at those indices, you see that they do not point at each other, so it's not valid. So let's have a look at this. So now I have my insert here where I store all the data. The insertion is always added the data columns at the end, so that is a pushback. And then I have to update the index and the reverse index, and you have different logic depending on whether the index is full or if there are free slots in it. This logic was damn difficult to get right. I would not have succeeded without fuzzing. It was challenging, let's say. The same with arrays, all this work to keep index and reverse index in sync. But the rest is fairly straightforward. As I showed, you get the from the row ID, you get the offset, and I have a separate angle brackets operator for just a pure offset also, and asking if a row ID is available. The rest is exactly the same as before. So if we run this, we see, 1.66 seconds, 1.56 seconds, 653 million cache references, 640, okay. This is worse. Why? Why is this worse?
Too much time in indexes.
Too much time in indexes, yes. Working on updating, keeping the index and the reverse index up to date is work. And this artificial workload that I'm giving it does a lot of removal of elements, which means that we move things to a free slot, which we did before, but we need to update the index and the reverse index, and that is work. And that is what we're seeing here in terms of performance, or drop in performance. What I did then was, which was it? Template. I did another thing. It's exactly the same, except I have a workload that just involves iteration. I'm not jumbling data around just to see what is the cost of having this when I'm not actually using it. So and this is intimidating because I made the logic a little bit too long, so it takes time, so now I can walk around on the stage and be really nervous about what we will see. But it's also better for showing actual differences, less noise in the results. Oh, I found a lot of stuff. Okay, so roughly 22 seconds for that one. And oh, I need to build it first. Okay. Is this the one time that it actually fails on me? That would be super interesting. Okay, 22. That was a little bit more than I expected, but it's 22.2. I believe that this is still measurement noise. In most of my runs, they have been more or less identical values. We get a little bit more when populating the structure, since we need to add things to the index and the reverse index, but then the iterations should be very similar. So we have a row ID. We can store something and get a key, get a row ID. We can look up the element by row ID, and I think that is good. That makes me smile. So let's crank up the successometer a little bit. This is good. We're onto something. But I really need an iterator interface. Otherwise, it's not fun. So we have to go into doing that. And one of the things that are important here is that even though we have a row ID here, we really, really want to iterate in storage order. Otherwise, the memory accesses will be jumbled all over the place. So we iterate in storage order. This is good for locality of references, but also because the CPU's prefetcher absolutely loves predictable access patterns. So this is good. So let's write an iterator. The value type of the iterator can be the tuple of references that we saw earlier used as a row with the operator angle brackets. And this is actually what's also used for if you use ranges. The zip view has the same idea. So there is a precedent in the standard library for using such a value type for iterators. So I can write iterators like this. I have a sentinel type that is just the marker of you have reached the end, and it's an empty type. It's nothing, but it exists as a type. And then the iterator. The value type of the iterator is the row. And I'm storing the table and the offset in the table. So the naive implementation would be to have a plethora of iterators here, one iterator for every column. But that would make the iterator unnecessarily large and make computations that aren't necessary, because maybe you only look at some of the columns, but you're still incremented in each of the iterators. So it's better to keep a pointer to the table or a reference to the table and an offset, because then operator ++ is just increment the offset. And our operator star to get the value is is very similar to how we had operator angle brackets before, but with only the offset here. I don't have to look at the indices. They are unimportant. So populate this tuple of references with each of the cells at that offset in every data column. And the equality comparison with the Sentinel is just to check, is this offset the same as the size of the table? This has an additional advantage that this iterator is safe to use in use cases where the vector grows, even if it reallocates the data, because you're doing lookup by index. And of course, if you didn't know this, from C++20 and later, if you do write operator equal in this case with the Sentinel, then you have them in the reverse order also. So you have operator equal Sentinel, comma, iterator. And you also have operator not equal. You get them for free by the compiler. So that is cool. So then our table, the addition to the table is almost laughably simple. We create begin and end. Begin returns an iterator to this table with offset 0, because that's where we start. And end just returns the Sentinel that is nothing. So let's have a look at this. So I have the row with the iterators, as I showed you, the operator plus increment the offset. And that is just it, and begin and end, and the horrible index juggling. But here, look. So I have a predicate, get a row, dereference it, check if start and z are what we want them to be. The found values are the values piped through the filter of the predicate. And then we loop over the found values and print them. Nice. This is mind-boggling. Why is it twice as fast? $6.3 billion cache references, 73 million cache misses compared to 63. Now, it cannot possibly be that. That is not enough. Prefetch is roughly the same, 500 billion instructions, 250 billion instructions, okay. CPU cycles 100 billion, 50 billion, all right. I think these are equivalent, but to the compiler, it's obviously different. It seems better suited to optimize code that follows patterns that uses loops over iterators, which the ranges filter does. Again, I'm definitely not complaining that I got twice as much performance by adding not a huge amount of code that made it easier to use. But I am confused. I'm not complaining. So we're almost there. The one thing I showed you earlier, though, was that it would be nice to, if I do a find an element, so I'm at an iterator, and I want to know which row ID is this object that I found. And a tuple of references does not really work for that particularly well. So what you can do is, of course, you can create a row type that inherits from the tuple, but then we don't really get access to the destructuring, which is a bummer. We want that is good. But the standard library offers ways to implement destructuring for your own types. So what you need to do is you need to specialize the tuple size for your type. So tuple size says how many elements does it hold. And you need to specialize tuple element of an index and T, and that is get the type of the IDX type of T. Try to say that. And you need to implement your own get. So get the IDX value from your type. And when you have done that, then you get destructuring for your own type. So let's roll a row type. Again, it looks remarkably similar to how the iterator looked like, doesn't it? Pointer to the table and the offset where we are. And now operator angle brackets gives us the row. And the row has a row ID type member function that looks it up in the reverse index from the offset. And the get function gets the ith member of the data columns, look it up at the stored offset. And the type is the indexing of the T's. That is a really cool thing in C++26, that you can do parameter pack indexing. It's very neat. It's also not very available, I'm sorry. But it's very neat. And then we create the specializations for tuple element. So the tuple element get the ith type of my T's. And tuple size is just the number of T's that there are. So now we can look at something. Yeah, Clang 14 does not have the parameter pack indexing, unfortunately, so I had to do an nth type to the recursive construction to look it up, but whatever. Soon, real soon. It's actually on the main branch for Clang, but it's not in Clang 18. The row type with all these goodies, and the rest is the same. No. Row. Now, in this workload, I'm actually not making use of looking up the ID. So this demo is only interesting in the sense of seeing what's the performance penalty for having this available, and it's nothing. But you have the ability. So that is nice. Check. One more goodie. So we're definitely home dry with the essentials. This is what we need for something to be nice to use, has good ergonomics and good performance. But I want more. I want a way to look at only a subset of the columns. I don't always want to look at all of them. So how can we select columns? So with the current, we can actually do that already by calling get instead of doing destructuring. So I can write a function that takes a table and loop over all the elements, and I call get of 0 and get of 3, like so. So it's there. But it's not very convenient, is it? I don't think it is. But that shows a way, actually. We can create a different row type. We can have a row type that says, I'm a row of a table of T's, and the columns of that table that I'm referring to are the C's. Like so. These are the columns, the subset. So with that, the intention of that is if I have I have this row of a table of int, char, double, and long with indexes 0, 2, and 3. The 0, 2, and 3 are the int, the double, and the long. And then I'm calling get 1. 1 is the one in the set of columns, or the array of columns, I guess you can say, which is the double. So with this, it becomes possible to select a subset. So I need an extra indirection here. So I have an array columns, all the C's, and I call get on columns of I to get the subset, to get the ith of the C's. I told you there would be indirections. So then the tuple size and tuple index becomes a little bit different. The tuple size will be the number of C's, not the number of columns in the table. And tuple element will be exactly the same as we saw with get, that we use this extra indirection to get the ith of the C's and get that type. Like so. So now I can write something like this. I want to select columns i's from a row, the row that has C's columns. And we do that by creating a new row, referring to the same table, but a subset of columns. So we can then write code like this, where I would say drop if x and z, select 0 and 2, because those are the ones I'm interested in. Return x is less than z. So I don't have to figure out names for the columns that I'm not going to use. And I think that's kind of cool, actually. And what more? I want to be able to select columns in a full iteration, a loop. I want to be able to write for auto angle brackets x, z, colon, my table, so select 0 and 2 of my table. So we can do this by creating a range selector template that refers to some range R and a set of columns C. And begin returns an iterator to using the begin of the underlying range, and end is just whatever the range's end is. And we keep a reference to the range. And to be able to do this, we need to know the underlying iterator, the range iterator, R iterator. That I can get that by calling begin on the underlying range. And then I can create my own iterator by publicly inheriting from that iterator, because then I get operator equals and operator plus plus, etc. for free. I don't have to worry about that. And my own value type is, we already saw how to do select on a row. And we know that dereferencing the underlying iterator is a row. So I just say, whatever the result of calling select these columns on that row, that is my value type. And operator star then becomes get the underlying iterator, call select on its value type. I'm standing here talking as if this was simple. You don't know how many gray hairs I got writing this and how many pages of compilation errors I looked at. But having iterated over this a number of times, it sort of becomes, yeah, sure, you just do this, you just do that, it's simple. It wasn't. It was absolutely not. But it's kind of neat. So then to be able to get there, we need some more dummy extra types. So the range selector maker it's just there to be able to have the pipe operator. So if you have operated pipe between a range and a range selector maker, you create this range selector that I just showed you. And then below that, you have the actual function template select that just returns the selector maker, which is kind of icky, but it's not the end of the world. So now I can write exactly that, what I said I want to write. For auto x, d, column values, pipe select 0, 3, and print them. This is cool. Really cool. So have the range selector with its iterator, the selector maker, and the select function template. And this logic here that I just showed you, this loop. Everything else is the same as before. And it's still 11 seconds. Yes. Cool. So, yeah, check one more. Successometer goes to cool. I'm getting quite happy with this. This is neat. This is really neat. So, but what I want, as I mentioned earlier, I want a way to call functions with the selected elements. That currently requires destructuring, which is, it's not the end of the world, but it's a bit unnecessary. So here I have this destructuring x of z from select of r. It's okay. But what if I had a function, a higher order function select that takes some function f and a number of columns, and that returns something that, when called, calls a function with the selected columns of a row? That would be neat. But this conflicts with the function template select that takes a row. I'm like, man, what have I done? What have I done? What have I done? What have I done? The compilation error message from this is really funny. You normally get like 10,000 lines of absolute gibberish. You don't. You get like 8 lines that says something completely irrelevant. It doesn't give the slightest hint of where the problem is. And that was a fun afternoon. But it dawned on me one thing. Well, what we can do, we should be able to resolve this conflict. So I can check, do a compile sign check. Is something a row type? So I have a variable template is row type, that it's false by default. And then I can have a specialization, specialization for row types and say that it's true. Did you know that you can do specialization on template variables? This is neat. And then we create a concept row type that is true for types T that fulfills the predicate. It is row type. So now I can write this. So this function is only valid to be called for f's that are not rows. I'm not happy with this. I'm not happy with this at all, because this is, I'm using a concept in a negative. I'm not saying call this for functions that are callable with rows. And I've scratched my head a lot trying to solve that, and I have failed completely. And I think it's actually not possible, but please prove me wrong. So I have to make do with this for now. Now, given that I actually have the row type, I may as well change the signature of the lambda that is returned to say that it is callable with a row type. So that makes the code a little bit easier to read. And now we can write the logic in a slightly different way. You see what the difference is compared to before? Select 0,2 of the function, and which returns something that is callable by a row, and we get just columns 0 and 2 as the row for this lambda. So this is nice, but it's not quite there to be useful yet, I think. So you know std apply from the standard library? It takes something invocable and a tuple, and it calls the invocable with the members of the tuple. So this is sort of the same idea, but it's a higher order version that you call apply with a function, and what it returns is something that is callable with a row, and then it calls the function with each of the elements of that row. So we keep the function, return a lambda. It is callable with a row, and when it's called, we call the function with each of the columns of the row. And then I can write drop if value, select 0,2 of apply this function, auto x and z returns x less than z, which is kind of nice. You recognize this thing? I think it has a name. It's called stdless. And I think this is awesome. I'm getting all starry-eyed here. This is super cool. So yeah, drop if select 0 and 2 with less. That is, if the elements of column 0 is less than the value in column 2, then we drop the values. So we can have a look at this. So the only really new things, this select that takes a function, and this apply that I just showed you. And then I can say, I have this predicate that just takes an x and a z. I don't have to do any destructuring. It takes two values, and I say, the fun values are the values that are filtered on columns 2 and 3 with applied to this predicate. And then the loop, as before. The attention. Yeah, still 11 seconds. Oh, it's good. So this didn't cost anything in runtime performance. Nice. So, yeah, check another one. We have that, and the hexameter is all starry-eyed here. This is nice. This is nice. And that is pretty much what I wanted to talk about today. If you found this interesting, you can go to this GitHub repo. It's a library that I'm playing with. Columnist, because you're manipulating columns of data. It is based on the ideas on this one. It is more sophisticated. It has, for example, you can do select on types. So if you're using strong types, say Matoush push MP units library, you can say select x position, comma, x acceleration, apply function, whatever. And it respects const, just such a small little detail. And there are a few other things. There's also, I have an experimental, I have a branch that is not yet at all finished. It's an embryo to what I believe will be an optimization, where instead of having a stud vector for every column, I just have one contiguous allocation, which should be faster when you grow the grow the table. But I only just got it to actually at all work yesterday, and it's faster with Clang using stdlib C++, but it's actually ever so slightly slower with GCC, and I haven't had time to even try to look at why yet. But I think we'll get there. If you have the time and the ability, please have a look, see if you can help out with something. There are things I want help with for just discussing the API. Is the API actually good? Is this the way we want it? I have some basics, like I would really like to have some benchmarking done in the CI so that I can immediately catch if I make a performance regression. If someone could help me with that, it would be awesome. They're also missing functionality. So if you have the time and the ability, please have a look and come with suggestions or questions. If you want to have a look at the code examples that I use in this presentation, they are there. It's important that you look at the correct branch because the main branch is for another conference which had issues. But it's there. You can use it. And yeah, that is all I had to say. Thank you. Three and a half minutes for questions. I'll go back to this one if you want to take photos. No one dares to ask anything. Okay, yes.
Have you tried this with any production systems or workloads?
Have I tried this with any production system? No, this is experimental. I have not. I wish to get there. I have used these kinds of ideas, but not exactly this. Other questions? All right. Thank you.